Today we will be exploring the chi-square test for independence. Let's clear something up from the get-go. It is pronounced chi-square, not chai. This isn't a latte from Starbucks, it is a mathematical concept. If you ever get confused, I like to think of the endearingly sociopathic character Kai from the Vampire Diaries, for those of you who happen to know what I'm talking about. Anyways, now that we know how to pronounce it, let's talk about what a chi-square test for independence is. As is indicated in the name, the chi-square test for independence, or simply chi-square test, is a form of statistical analysis which measures the level of independence between two factors, which is much less confusing than it sounds. All that means is that the chi-square test for independence uses data to determine how closely related two things are. For example, we could take data on how many car accidents teenage boys were involved in and how many car accidents teenage girls were involved in, and use this chi-square test to see if gender plays a role in the differing numbers. In this case, our alternative hypothesis would be that car accidents involving teenagers are dependent upon gender. Alternative hypothesis is represented by the letter H, subletter A, and is basically the concept we are testing. It is the hypothesis that we want to accept. On the other hand, the null hypothesis is boring, and we do not want to be unable to reject this null hypothesis, because this means that our alternative hypothesis is untrue. In our current example, the null hypothesis, which is represented by the letter H sub 0, is that car accidents involving teenagers and gender are independent. Does that not sound incredibly boring to you? Of course it does. We want controversy. So let's see if we can accept the alternative hypothesis. Here we have a chart that shows motor vehicle crash deaths among 13 to 19-year-olds in 2011, 2012, and 2013. This is actual data taken from the Insurance Institute for Highway Safety. All of this data you see here are the observed values. They are the numbers that were actually calculated and thus observed. We need to calculate the expected values, or the values that one would expect to see when using the total numbers of male and female crash involvement. To find the expected value of male deaths in 2011, we would take the total number of male deaths over the total number of deaths for both genders, and multiply this by the total number of deaths in 2011 over the total number of deaths for both genders. This is because we are calculating the probability that the person was male and the probability that the death happened in 2011. Therefore, we put 5,498 male deaths over 8,389 total deaths, and multiply that by 3,032 deaths in 2011 over 8,389 total deaths. This calculation turns out to be 0.23687. Make sure to include as many decimal places as possible in order to maximize accuracy. This number is the probability that the person who died was male and that they died in 2011. Now, we have to multiply that probability by the total number of deaths, which will bring us to our final expected value. If we multiply the probability by the 8,389 total deaths, we should get 1,987.118 expected male deaths in 2011. Again, make sure to include as many decimal places as possible. Now we need to calculate the expected values for all of the other data points. Let's do one more together. When we calculate the expected value of female deaths in 2011, we will repeat the same steps we took the first time. Total number of female deaths over total number of deaths, multiplied by the total number of deaths in 2011 over the total number of deaths. The expected value probability that you should get is 0.124553776. Remember to include an abundant amount of decimal places. After multiplying that number by the total number of deaths, our expected value for female deaths in 2011 should be 1,044.881631. I recommend pausing the video now and doing the rest on your own, following the same pattern we've been doing. I've gone ahead and filled in the chart with our expected values for each data point. Now we will be using both the observed and the expected values in order to find the chi-square statistic. The formula we will be using is as follows. The uppercase sigma sign, which looks like a fancy E, means sum. So we take the sum of observed minus expected value squared divided by the expected value. We perform this operation of observed minus expected squared divided by expected value for each data point, and then add each of those answers up, and we should get our chi-square statistic. So for male deaths in 2011, we would subtract 1,987.118369 expected deaths from the actual 1,991 observed deaths. We get 3.8816, and then we have to square it. The reason we square the observed minus expected value is in case the number comes out as negative. Squaring a negative number would make it positive, and we want to work with positive numbers only. So we square 3.8816 and get 15.067057. This divided by the expected value is 0.00758237. We repeat this same process for each data point. So for female deaths in 2011, we would subtract 1,044.881631 expected deaths from 1,041 actually observed deaths and get negative 3.881631. This squared is 15.06705922. We divide that by the expected deaths and get 0.01441,987. I recommend pausing the video now and doing the rest on your own following the same pattern we've been doing. Now that we've found all of our values, we have to add all of the numbers we've gotten together. Our chi-square statistic is 0.3536. Unfortunately, that one value doesn't tell us much about the dependence or lack thereof between gender and teenage crash involvement. We now have to see how many degrees of freedom we have. The formula for degrees of freedom is number of rows minus 1 multiplied by the number of columns minus 1. Rows and columns is referring to our original table of data. So if we go back to our table of crash deaths, we will see that there are 2 rows of data and 3 columns of data. Therefore, 2 rows minus 1 times 3 columns minus 1 is 2 degrees of freedom. Let's think about that conceptually. Assume we know the totals for each row, but not each individual data point. If we choose to have 2,000 male deaths in 2011 and 2,000 male deaths in 2012, then in order to fill the total that we are given, there has to be 1,498 male deaths in 2013. Therefore, we only have 2 degrees of freedom in each row because we could only choose the amount of deaths 2 times. We repeat the same process for the columns. If in 2011 we choose to have 2,000 male deaths, then we have to have 1,032 female deaths in 2011 in order to fill the column total. That gives us 1 degree of freedom. 1 degree of freedom times 2 degrees of freedom is 2 total degrees of freedom. On the bottom of this graph are the chi-square statistics. Our statistic is nearly 0, so we look at the far left end. Since our data has 2 degrees of freedom, we look at the blue line labeled DF, or degrees of freedom, equals 2. Where the blue line and our chi-square statistic meet tells us approximately what our p-value is. The p-value is the probability that the data occurred by chance, or randomly. Looking back at the degrees of freedom graph, we can see that our p-value is probably going to be very high, since the blue line is very high above where our chi-square statistic is. In order to find the exact p-value, you have to use a graphic display calculator. Find where your graphic display calculator says matrix. Go to that and edit the first list. Put in all of our original data points and then press enter. Then find where your graphic display calculator says stat. In stat, there should be a column labeled tests. Go to tests and scroll down to find the chi-square tests, and it usually uses the symbol for chi-square. Go to that, press calculate, and the calculator should calculate both the chi-square statistic and the p-value. The calculator tells us that the p-value is 0.905, or 90.5%. This value must be compared with the significance level. The significance level of either 10%, 5%, or 1% also states the probability that the data occurred by chance. But when performing a chi-square test, one usually picks a significance level beforehand. If the p-value exceeds the chosen significance level, then the data is probably independent, and one would be unable to reject the null hypothesis. Since our p-value exceeds all three significance levels, it's a safe bet to say that the data is independent, and we are unable to reject the null hypothesis, which means that, according to this data, teenage crash-related deaths and gender are independent.